So previously we have given geometric realizations of central simple algebra. We had a bijective correspondence between central simple algebra of degree n over k and Severi-Brauer varieties of dimension n over k. Right, so given a Severi-Brauer variety x over k, we can associate to it some central simple algebra and thus an element of the Brauer group of k, which I will still denote by x with a bracket. Now, then naturally we'll have a few questions. For example, let's say we have two Severi-Brauer varieties x and y. When are the corresponding class of x and y in the Brauer group equal? In other words, we want to have a geometric characterization of Brauer equivalence. Now, another question is, how do we recharacterize the algebraic invariance of the central simple algebra, right? A central simple algebra has several invariants, for example, the index, the period. How do we recharacterize that in terms of the geometry of its corresponding Severi-Brauer variety? In this video, we are only going to give the geometric characterization of index and Brauer equivalence because the answer to both of these are going to rely on the definition of a specific class of subvarieties of a Severi-Brauer variety called the twisted linear subvarieties. So given a Severi-Brauer variety x, we are only interested in a very specific class of subvarieties. Now, by definition of Severi-Brauer variety, x is gonna split over some finite extension of k, but that means in particular that x must split over the algebraic closure of k, right, k bar. So we're interested in the subvarieties y of x that are also Severi-Brauer, such that the inclusion of yk bar into xk bar is compatible with the identification of xk bar as a projective space. In other words, this corresponds to an inclusion of a linear subvarieties of the projective space over k bar. So what's special about these subvarieties is that if y is a twisted linear subvariety of x, then the class of y is actually going to be equal to the class of x in the Brauer group. And this gives us a way to define Brauer equivalence geometrically. So we claim that if we have two Severi-Brauer varieties x and y, then they're going to have the same class in the Brauer group if and only if there exists some Severi-Brauer variety z such that x and y can both be embedded at twisted linear subvariety of z. Right, and the sufficiency here is obvious from what we just mentioned, because if x can be embedded as a twisted linear subvariety of z, then that means from what we just discussed that the class of x must be equal to the class of z. Similarly, if y can be embedded as a twisted linear subvariety of z, then the class of y must be equal to the class of z in the Brauer group of k, so the class of x must be equal to the class of y. Now it's a necessity part that requires a bit of work. Given two Severi-Brauer varieties x and y having the same class in the Brauer group, how would we construct some Severi-Brauer variety z such that x and y embed into z as twisted linear subvariety? Now how do we do that? Well, for that we need to use the following proposition proven by Michael Artin. So let's say that A is in a central simple algebra corresponding to x. Then we can take a matrix algebra over A. You can choose R to be any positive integer. And then we can look at let Z be the corresponding Severi-Brauer variety corresponding to the matrix algebra MRA. Then the claim is that we can embed x as a twisted linear subvariety of Z. This will then allow us to prove the sufficiency of the geometric characterization of Brauer equivalence. But we're not going to discuss the proof of this here. We're going to move on and use this to give a geometric characterization of the index. So the claim here is that the index of the central simple algebra associated to x is going to be equal to d plus 1, where d is the dimension of the minimal twisted linear subvarieties of x. So all of these minimal twisted linear subvarieties of x are going to have the same dimension, and it's going to be equal to the index of the central simple algebra associated to x minus 1. For short now, I will just call this the index of x. Now for the proof, we want to use the following lemma. So let's say Y is a Severi-Brauer variety corresponding to a central simple algebra B. Then observe that Y is minimal if and only if B is a division algebra. And why is that? Well, so here we have to recall that the dimension of Y is just going to be equal to the degree of B minus 1. So then, therefore, the dimension of Y is minimal if and only if the degree of B is minimal. But now remember, by Severi-Brauer's theorem, we can write B as isomorphic to some matrix algebra over some division algebra D. Right? D is going to be the unique division algebra in the class of B. So this means in particular that the dimension of B over K is going to be bigger than, greater than or equal to, the dimension of D over K. But the degree of B, by definition, that's just the square root of this dimension. So we see that the degree of B is going to be greater than or equal to the degree of D. So then the degree of B is minimal if and only if B actually equals to D. So B itself must be a division algebra. So now let's come back to the proof. Let's say Y is a minimal twisted linear subvariety of X. Then by our lemma, we know that it must correspond to some actually division algebra, D. And degree of D is just going to be dimension of Y plus 1. On the other hand, previously we know that the class of X must be equal to the class of Y in the Brauer group. In other words, D is the unique division algebra in the class of X. So by definition of index, the degree of D is just the index of the class of X. And so we see that the index of the class of X is going to be dimension of Y plus 1. And that's exactly what we wanted to prove. So all the minimal twisted linear subvarieties of X are going to have the same dimension, and that dimension is going to be equal to the index of X minus 1.